speaker of the morning is Mark Hagen, and he'll be telling us about cubings and asymptotic cones.
Thank you very much, and thanks very much to the organizers for inviting me. I realized last night while I was writing my notes that we did quite a lot of work on this thing that I'll talk about at the last INI program in 2017. So that's grim. Everything I'm going to talk about today is joint work with Montse Casals-Ruiz and Ilya Kozachkov. Yeah, so some sort of work in progress, but you know, some sort of draft can be found on my website if you're interested. So, so what I'd like to talk about, I'll make a little outline. So, the zeroth thing is the question about uniqueness. Of asymptotic cones. Next, I'm going to state my theorems. So there'll be 3 theorems I'm going to state, and then my responsibility will be to tell you what the things in the theorems mean, and maybe the idea of the proof. And then I'm going to mention the two sort of main ingredients of the proof. So one is the notion of a real cubing, and then the last thing I'll talk about is universal real cubings. So real cubing is a sort of very specific higher rank generalization of a real tree, and then a universal real tree, a universal real cubing will be you know, just as there are universal real trees that are determined by local information, namely the valence at each point, it generalizes in a slightly more complicated way to universal real cubings. Okay, so I'm going to state the question over here. So let's talk about asymptotic cones for a second. So I'll recall the definition so I can illustrate. You know, the question is about the definition actually. So X is the metric space that we want to study. Typically, Kelly graph of a finitely generated group, and then we're going to fix. I'll call it ON. A sequence in X. So that's the sequence of observation points. Typically we're going to be interested in the case where X is a group, and there's no loss of generality for our purposes in assuming that that's just a constant sequence at the identity. So that's a choice that we're making, but it's, you know, in our applications is not a very important choice. And then there are 2 more choices that we make which are important. So call Rn is the rescaling sequence. So that's an increasing unbounded sequence of positive real numbers. And then omega is a non-principal ultrafilter on the natural numbers. So these 2 things I'm highlighting as things we decide in advance. I'm going to write down the definition of an asymptotic cone of X, and it has those things in the definition, and they matter in general. So let's write. So the cone, I'm usually, even though the whole business over here is how much and when those things matter, I'm usually not going to write them when I write the asymptotic cone, but I will right now. So let's say like cone with respect to the sequence Rn and the ultrafilter omega of x may be based at the observation points On, which I'm going to usually abbreviate just cone of x, having fixed all those choices, is so you look at all of the sequences in X that are at finite rescaled distance from the base point. And then you take the ultralimit, and you have to get, that's what it means to be at finite distance. And then we just quotient by distance 0. So I'll write it down what the metric is. Oh, yeah. Yeah, so you just rescale the metrics. You just think of a sequence of metric spaces that are just the one you started with, but rescaled by the rescaling sequence, and then distances are just ultralimits, and then you just take the metric quotient of the pseudometric space you get. Okay, so that's the asymptotic cone, and I think I don't have to talk super much about why we're interested in asymptotic cones, but I kind of think of there being two worlds of reasons why you're interested in asymptotic cones. You might be interested in an asymptotic cone of a group because you want to study like limiting actions. So maybe you have like sequences of homomorphisms from a group H into a group G, and you can use those to make an action on H on an asymptotic cone of G. Maybe G is hyperbolic and you're trying to like prove something about splittings by getting an action on an R tree. The other reason why you might be interested in asymptotic cones is because you can use them to study sort of, they make coarse geometric things become fine geometric things, because what you're doing is, apologies to people who heard this joke a couple weeks ago, but like, I just take off my glasses and then I see the asymptotic cone of like the podium over there, like all the little sharp features of it, all the little local features of it vanish, and I just get this blurry object from infinity. So you might want to use that. You might want that point of view if you are studying quasi-asymmetric rigidity and you want to turn all your quasi-isometries into bi-Lipschitz maps and have things be continuous and stuff like that. So those are kind of two reasons, or two vague reasons why you might be interested in asymptotic cones. But now I'm going to go over here and I'm going to write the question, and I'm not going to use the board below. So the question is if X is Cayley graph with respect to a finite generating set of a group G, how does the cone of X depend on the ultrafilter and the rescaling sequence? So the answer in general is a lot. So maybe I'll just say some results in that direction. So first of all, what do I mean when I say, like, what's the best thing you could hope for? So if I'm interested in studying, the asymptotic cones of a group G, I don't want to privilege one generating set over another one. So I'm really looking at the quasi-isometry class of spaces when I'm looking at G. And then quasi-isometries become bi-Lipschitz maps when you go to asymptotic cones. So the best sort of answer you might hope for would be that you have a group G, so that any two asymptotic cones of it are by Lipschitz equivalent. Maybe I'll write that down as a definition so that I don't have to write it later. Foreshadowing. So G has unique cones, like in a very strong way, if any two asymptotic cones are by Lipschitz equivalent. But there are lots of groups that have highly non-unique asymptotic cones. So if you haven't seen it before, there's a really short paper by Thomas and Velikovich where they do like an infinitely presented small cancellation thing, and they like make a very explicit construction of a group with different, where when you vary the ultrafilter or the rescaling sequence, you get non-homeomorphic asymptotic cones. So they super fail this. And then like Osen, Olshansky, and Sapir, in fact, like studied the class of what are called Lacunary hyperbolic groups where, some of the asymptotic cones are real trees and some of them are not even simply connected. There's results of Drutu and Sapir who made examples like just horrific examples where you when you vary the ultrafilter, you get like continuously many homeomorphism types of asymptotic cones. Horrific in a good way. And sorry?
The cones are horrific because they're not locally compact most of the time.
Right. Yeah, that's a good point. So typically, except in very limited cases like nilpotent groups and things like that, they're not locally compact spaces, and you can play like cardinality games and do crazy things. So I think my favorite way to shock people when you give this sort of introductory spiel about asymptotic cones is that is the fact that like SL3Z, there's a result of who is it? Kramer, Schella, Tent, and Thomas, I think, that says that depending on whether or not you accept the continuum hypothesis, like SL3Z either has unique cones or it has uncountably many non-homeomorphic cones. So like it's kind of a wacky endeavor. Now, like maybe I'm going to write some positive results over here though. So. So, so by that I mean groups that have unique cones. So hyperbolic groups so in fact have very unique cones. So all, maybe I'll write the word non-elementary so that the next thing I say becomes correct. So that all of the cones are actually isometric. So the universal, like, uncountable valence real tree. And then Osen and Sapir, and also Sisto. So these papers are quite important to the theorem that I'm going to state. So they proved the result for relatively hyperbolic groups that one would expect. So if the parabolic subgroups all have unique asymptotic cones, then so does the group, where unique means in the sense of like by Lipschitz equivalence. So Sisto used that and a bit of other stuff to show that if you have like a compact connected orientable three-manifold, then the fundamental group has unique asymptotic cones. So he's looking at like, first in general, this fundamental group is relatively hyperbolic, and so he can use this once he knows how to do graph manifolds, basically. And then he's looking at the JSJ and doing a complicated thing. So those are there's more examples, but those are the kind of ones that are going to motivate. We're thinking about things that are sort of in this spirit. And then the question that we're after, so this is due to Sapir, and I found it in a paper of Bairstock also. So what if G is a right-angled Artin group, or the mapping class group of like a finite type orientable surface? So that's like, are the cones of these groups unique? And I don't know exactly what the motivation was, except that there's a result that I'll talk about mapping class groups where, like in the course of proving things like QI rigidity for mapping class groups, people sort of understood quite a lot about the asymptotic cones of mapping class groups, and I think sort of understood quite a lot of R-tree-like features in those asymptotic cones, and had the idea that maybe the same type of thing that works for hyperbolic groups could maybe work for this extremely non-hyperbolic group. So that's the question, and I'm going to leave the question there, and then I'm going to take a poll of how far. Can we see that far? Okay, so
I have a quick question
yes.
before we turn away from horror.
Yes.
So in this result by Shala and others, do you know, so you said that if the continuum hypothesis fails, you can have uncountably many?
Yeah.
Do you know what the cardinality was?
I think it's continuously many.
No.
It's, oh no, it's two. Yeah, you're right. You're right.
It comes from out of difference. You have R omega that are non-asymptotic, and you have that many omegas, which is why many of you didn't choose logic.
Thanks for me.
But also to add a bit of horror to this positive stuff, do any of these results depend on the continuum hypothesis? Or?
No.
So if you accept the continuum hypothesis that the maximum asymptotic cones that are non-isometric is probably given, and our for an example actually reached that in, if you really want to know this stuff.
Thank you.
Yeah, that's a good question though, because that's sometimes sort of, that issue kind of is lurking. Sometimes we at various points thought that we needed to say stuff like that in order to have the following theorem, but we don't. So I'll state three results. Put the main one above the line, so we'll call it theorem 1. So let's let G be a group which is quasi-isometric to one of the following groups. So pi 1 of x, where x is a compact special cube complex. So for instance, a RAG or a right-angled Coxeter group, as we heard about in Chris's talk yesterday. Mapping class groups. And there's a few more that could go on this. Maybe I'll write a couple more. Extra large type Artin groups So that's some class of Artin groups that have a lot of sort of hyperbolic behavior. And maybe I'll bravely say it, although I haven't explicitly checked this one yet, but if you take the mapping class group and you quotient by the set of all Dane twists, by the subgroup generated by all the Dane twists, and a suitable large integer, then this group should fit into the class of groups for which this theorem holds. And there's various other examples, and I'll talk about why this sort of disparate class of groups can all be handled at the same time. So then G has unique cones. So that's the statement. So that answers the question. And then what I want to actually talk about is two results that that feed into the proof of that. So basically, so the proof of theorem 1 is just like a brute force proof. You just have to like understand the whole structure of the asymptotic cone and then know enough about it that that you can prove that. Like it's not very slick. So what I mean by that is the following two things. So theorem 2 says that if X is a hierarchically hyperbolic space, there's a little dead center here. Void. Then any cone of X is by Lipschitz to what's called a real cubing. So I need to tell you. So part of the goal is to tell you what that is, so we know what this says. So this is the real cubings are some class of spaces that I'll define in a bit. This theorem does not like say anything about the uniqueness yet, though, and in general, since I haven't put, this isn't a group, this is just a space, in general, which real cubing you're looking at does vary with the ultrafilter and the rescaling. It's easy to like make non-co-compact examples where you can mess around with things and get different asymptotic cones. So this just says for each choice of ultrafilter and rescaling sequence, you get one of these R cubings, which is by Lipschitz equivalent to the asymptotic cone. But in the setting, so if G is a, I'm going to say some words that aren't going to come up again, but a colorable hierarchically hyperbolic group with, I'm going to do this. Co-compact product regions so before I say the conclusion, so a hierarchically hyperbolic group, you all know what that is, because I'm not going to tell you. But you should know, seriously, you should think about like the mapping class group of a surface, and you should think about the fact that the surface has lots of subsurfaces. Each one has a curve graph, and you have subsurface projections from the mapping class group to all of the curve graphs of all of the subsurfaces, and those projections are equivariant in the way you'd expect. So like mapping classes take subsurfaces to subsurfaces, and that commutes with subsurface projections. Being an HHG is just a generalization of that. Colorability, I'm probably not going to talk about it. But I will tell you what it means in the mapping class group. In the mapping class group, there's Vesvina, Bromberg, and Fujiwara showed that you can find a finite index subgroup so that two different subsurfaces in the same orbit aren't disjoint. And colorability is just abstracting that fact. So that's an extra condition you can put on an HHG. And then the co-compact product regions business, actually, it was at this place in 2017 when we figured out that that doesn't follow from the hierarchical hyperbolicity axioms. So that is asking that, so the mapping class group satisfies that because the product regions are the cosets of the multi-curve stabilizers. So you have some subgroups that are quasi-isometric to products. That's the product region thing. And you have to take all the translates of those. Those are product regions in a hierarchically hyperbolic space. And they kind of, I'll talk about them more in a bit, but they kind of see all of the failure to be hyperbolic, lives inside a product region. And this is asking that the product regions are actually subgroups. So it's kind of like the fact that in a relatively hyperbolic group, the peripherals are actually like subgroups. They're not just random nice subspaces. In the relatively hyperbolic setting, that's automatic. In this setting, that's something you have to assume. But it holds in all those examples. So maybe I'll even, before I'm aware that I haven't stated the theorem yet. I'll finish stating it first. Then any cone G is by Lipschitz to the universal real cubing determined by its local structure. So that's a bunch of words. So again, in this theorem, there's not yet anything about uniqueness of the cone. So it just says that you take an asymptotic cone. Theorem 2 tells you that it's this thing called a real cubing, which can depend on the ultrafilter, and a priori it can depend on the ultrafilter here. The local structure of a real cubing is the thing I'm going to define, from that data, one can build just from knowing this abstract thing, one is going to be able to build a real cubing just out of this information, which doesn't remember that it came from an asymptotic cone. This is just an abstract space. And by sort of gluing together copies of this thing, one gets this object. And so the point of this theorem is that you can recover the cone from knowing something about a subspace of it that doesn't remember that it's the cone of that group. So the idea behind this theorem is to reduce the question about uniqueness of the cone to the question about uniqueness of this tiny subspace of the cone. So I'm going to say this in more detail, but that's the idea. So the way that these piece together to prove that is that you first get a real cubing structure on your cone, a priori depending on the ultrafilter. You extract some local information from it. That local information a priori depends on the ultrafilter. You build this object in a way that is just completely abstract. It doesn't depend on the ultrafilter or anything besides that, like to any greater extent than this does. And then and this will tell you that as long as the local structure was independent of the ultrafilter, then so is the cone. So I have to tell you what all these things are, but that's the overall strategy. I'm not going to talk about the proof that the local structure is independent of the ultrafilter, but I'm going to try to talk about a bit about what this means and how at least what the local structure is. So now I can tell you about real cubings.
Can you follow about implying trees? Was it not
Yes, yes, by a theorem of Harry, who is over there. In fact, colorable, so what Harry proved was that a colorable HHG has a quasi-isometry to a cat-0 cube complex, which coarsely preserves the median. So it's like, I think, kind of an amazing fact about the mapping class group, because I used to think it was false. But yes. So actually, right, that is a good. So Cornelia just asked about quasi-asymmetrically embedding certain hierarchically hyperbolic spaces into finite products of trees. And that is a thing you can often do. And real cubings are all about asymmetric embeddings in products of trees, but not finite products. So we're going to be mostly talking about things sitting inside infinite products of trees. For reasons that I think I can explain. So, yeah, so let's tell you what our cubings are. All right, I'm going to start by recalling what a median space is. So if you have a metric space, its median, if you have this ternary operator mu, which takes, so such that whenever you take a triple in X, you look at the metric intervals between each pair of points. So the interval between X and Y is the set of points W, so that the triangle inequality becomes an equality. And being median means that for any triple, the intersection of the three intervals that you get by looking at pairs consists of exactly 1 point, and that's the median. So that's the median space. And the examples that we need, so real cubings are going to be a subclass of median spaces that you get by solving a system of equations inside an infinite product of real trees. That's what I'm going to try to explain. So, so first, real trees are median, and the next example I'll describe is, so let's I'm going to use fancy F to be a certain, some set of real trees. And emphasize that in practice this is usually going to be an infinite set, and for each real tree, we're going to pick a base point. I'll call it 1 sub u in the real tree u. And then you can look at the product. I'll denote it L1 of F. You can look at the product of all the real trees with the L1 metric, but you just consider the component containing the base point. So this is that's the set of points in the product that are finite L1 distance from the base point. And so the metric you give it is just the L1 metric. And then the median on the product is just defined component-wise, so mu of define the component-wise median. So that's a median space. In general, it's well, I'll define the notion of dimension that we use, and then I can say it's infinite dimensional. So two definitions. So a subset of a median space is a median subalgebra. I'm hiding the notion of a median algebra, but it's poking out in that terminology. So it's a median subalgebra if it's closed and they're taking medians. And then we say the rank of X is the supremum of natural numbers n, so that write it first. Right. So if you look at like a discrete space with 2 points, that's a median space. If you take the product of a bunch of copies of it, that's a median space again. And then you can just check. You can look at copies of such spaces embedded as subalgebras of X, and the largest dimensional one is the rank of X. So, for example, if these real trees are, if infinitely many of these real trees are not just points, then the L1 space has infinite rank. Infinite rank median spaces are really weird, but we're going to actually focus on finite rank subspaces of this thing. So, right. So I'm going to define real cubings constructively. I decided. So, so we're still working in this setting, and let's. So for each. Remember, I said that a real cubing is going to be a solution set to like a system of equations, or a system of conditions inside the L1 product of all the trees. Those are going to be conditions on pairs of coordinates. So for each pair of real trees, impose one of the following. Well, let me say it a different way. Let me say define, I'll say X of U comma V subset of the product of U and V to be one of the following. And I'm going to draw some cartoons. So, so here's U, here's V. And the first situation, I could take just the whole product. And in this situation, and we describe this, if I choose this situation, I'm going to say that U and V are orthogonal. I'm just going to take a bunch of, like for each pair, I'm going to take a bunch of subspaces of, I'm going to take a subspace of the product of those two real trees. I'm going to intersect all the preimages of those subspaces upstairs in the whole product and see what I get. And so right now I'm just defining the three possibilities that I'm allowing myself to impose for a pair. So another thing I could do is I could delete some quarter spaces from the product. So this means that inside the real tree U, I pick a point associated to the real tree V, which for ancient reasons is called rho VU. So the point associated to V inside the tree U. And over here, I have rho UV. And then the subspace I'm choosing is the orange subspace. And it's the set of places where, you know, it's a set of XU, XV, so that one of the two coordinates agrees with my special point. So in this situation, we say U is transverse to V. And then the final situation that you could do is not symmetric. Here's U and V. And in this situation, I'll call it U is nested in V. And over here, we again, inside the bigger one, inside V, we have a point associated to U. And the way to interpret it is that, like, if my V coordinate is there, I'm allowed to move wherever I want in U. But if I want to move in V, I'm sort of stuck in different places. So my orange subspace is that. So those are all, so each of those orange subspaces is a median subalgebra of the product of those two trees. And because the median on the whole thing is the product is defined component-wise, the natural projection from the L1 product of all the real trees to the product of each pair preserves the median. And so when I take the pre-image of a subalgebra, I get a subalgebra. So from an intersect over all pairs of distinct real trees, the pre-image under the natural projection to that pair. And I get some subspace of the L1 space. And this is always a median subalgebra. So one comment is I didn't define the things very carefully over there. I think it's sort of clear what the conditions would be if the real trees involved were all lines, and I can get away with it because it turns out to be the case that one can always assume that. We never use that fact, but you have to just let me get away with being imprecise because I was actually kind of precise. Like, those are pretty literal pictures in the plane, and so you can literally have that in mind, that example in mind, and you won't be losing any generality. Although typically, we are going to realize the same thing inside a product of more complicated trees. But
what is pi?
Oh, sorry, pi, thank you. Pi, I just mean, so this is the natural projection from the full product of all the real trees onto the product of those two. Okay, so that's a median subalgebra, and then we say the following. So X is a real cubing. That X is a real cubing if it satisfies the following things. So as defined, it could be empty, right? If I made my choices wrong for different pairs of things, I probably made the empty set. So I want my base point, which I'll call 1, which is just the tuple of base points in the trees. I want to insist that that belongs to X. And X is complete and connected. So here by complete, I mean the metric on X is just the subspace metric it inherits from the L1 space, and since it's a median subalgebra, X, right, X will be a median metric space. And what else do I need from this, the way I set it up this way? So there exists like n such that if U1 up to UK are all nest related or all orthogonal, then K is at most n. So it turns out that you can check directly from this. I didn't define nesting carefully enough. But it turns out that you can check that nesting is a partial order. And so here you're sort of bounding the length of chains, and then orthogonality, yeah, it's just some relation, and you're bounding the size of clicks in there. And
excuse me.
yes.
What do you mean? This sign, is it?
This one?
Yes.
Oh, sorry, that's. I guess I wrote it like this.
Okay.
Yeah, because you can have a lot of copy. Yeah. Right. So, right. So, in fact, this is going to imply the rank. I think this is kind of intuitive. The rank of X as a median space is actually bounded by n. The only way you get cubes in X is by having pairwise orthogonal sets there. Every time you have two factors of the tree obeying one of those other relations, you're kind of cutting out most of any cube that you want to see. But you get n cubes from collections of n orthogonal things. So we want those two things, and then that's a real cubing. There's several, so there's 3 co-authors, and so there's 3 equivalent formulations of the definition. So the one that we tend to, this is kind of actually my conceptually favorite one, because Ilya figured out that you can really pretend all the real trees are lines without using a trick about embedding real trees into like actual L1 spaces. And so this definition is kind of easy to present. The definition that we actually work with is much more like the definition of a hierarchically hyperbolic space, except you're replacing all the sort of curve graphs with real trees, and you're replacing sort of all the coarse geometry with fine geometry. So all the little constants in the definition of a hierarchically hyperbolic space become 0. So it's like a simplified version of that for people who are into that sort of thing. I have like 2 minutes left. But now you know what a real cubing is. So I am going to tell you quickly, because now I can tell you fairly quickly, how to prove theorem. Theorem 2. So theorem 2. So theorem 2 is inspired by a result of Berstock, Drutu, and Sapir, who proved that the asymptotic cones of the mapping class groups are real cubings. They didn't say that word, but it's all in their paper. So what they did was something a bit different than what we did, but it constructs exactly the same thing. So they started with the mapping class group of the asymptotic cone of a mapping class group, and they made a bunch of maps onto real trees, so that the product of all those maps was an embedding, and they concluded from that the asymptotic cone is a median space. And so our proof in that setting constructs exactly the same trees in a different way, but now starting with the knowledge that the thing is a median space, which is provided by other means. So, I'll just write the steps for theorem 2. So the first thing is that so Bowditch tells you that the cone of your hierarchically hyperbolic space, so think of the mapping class group, is by Lipschitz to a median metric space. And by different means than the Verstock-Drutu-Sapir result. So more or less, a hierarchically hyperbolic space, sort of by definition, coarsely injects into some infinite product of hyperbolic spaces. Subsurface projections applied to the mapping class group, sit it inside the product of all the curve graphs of the subsurfaces. And that looks a little bit like that L1 situation over there, except it's coarse geometric. And you can pull back like what's called a coarse median to the mapping class group. So now you have this ternary operator that obeys some very coarsified version of the definition of a median space. And what Bowditch did, actually, this is my favorite part of the whole business. This is a really beautiful argument. It's really short. So he says you have this coarse median on the space, so you go to the cone, you get this candidate for being a median operator, but the metric is wrong, and then he changes the metric on the cone within its by Lipschitz class so that it's on the nose of median metric space, and we take that as our input. And then the second step is I have to make maps from the cone to some arteries. So once I've made a bunch of maps from cones to arteries, then I'll like sufficiently many, then I'll have sat it inside a product, and then I can check these conditions. So I'll tell you just how the maps work in one sentence. And the way the maps work is that you collapse ultralimits of product regions. So I wanted to get just that far so that I can mention like the main tool. So in the mapping class group or in an HHS more generally, you have those product regions I was talking about. So you can think of multi-curve stabilizers. And when you pass to the asymptotic cone, you have ultralimits of sequences of those things. And those are now convex median subalgebras, and they are actually isomorphic to products. Like the sort of coarse product structure becomes a fine product structure. And hierarchical hyperbolicity tells you that in the cone, all of the higher rank behavior lives inside these product regions. And then, so if you collapse them in an appropriate way, you're going to get a new median space where all of the higher rank behavior is destroyed, and that's an R tree. And the last thing I'll say is that the collapsing thing is a little bit delicate, and that relies on work of Fioravanti about measured half spaces. I am way over, I'm sorry.
So I wasn't sure I understood whether the cubing you get, the cubing you get in the end is finite rank or not?
Yeah. So the rank will be like the same as the
number of trees which you can get.
So the number of trees is infinite, but the subalgebra is like much smaller than the full product. So the idea is that like families of trees that are orthogonal that actually give cubes inside the subalgebra are of bounded cardinality. Like you can't independently move in infinitely many different factors starting with. Does that make sense? Yeah. You had a
I had another question, but it's
okay. Yeah. Henry.
Is there some notion of co-special action on a real cubing? Is that like? I mean, I'm not just totally making this up because before this definition of real cubing, there was an earlier definition of real cubing. I think, like they were honestly.
Yes.
And there they definitely talked about co-special.
Yes.
Things.
So
I'm wondering if that somehow extends to this new, more general setting.
yes, I think it does. I think you should also, the guy next to you probably also has a lot to say about
I
that.
think, yeah, there are.
But yeah, that's something that we're thinking about. Kasha, I think you.
So when you said theorem 3 is like universal R cubing, is that unique?
Right, so I didn't, because I am poorly organized today, I didn't talk about those. So basically, it's
But, like,
determined by,
which type, or
what's that?
is it unique by which is type?
So it has a unique like isometry type. So if I give you a real cubing and you stand at the base point and you look where you can go by only changing like, you know, one coordinate, that will give you like the stuff you can see sort of locally in the real tree. And that's enough information to determine what, like a universal real cubing is a bigger real cubing that's constructed using just that piece of the real cubing you started with. So like, and then it's uniquely determined up to isometry by that information. Does that answer?
And so this theorem 1 follows from theorem 3, like all those groups like colorable HHGs? Or?
So those are, right, so those groups are all colorable HHGs that satisfy the thing. So theorem 1, so theorem 3 reduces theorem 1 to the question of, does the local structure of the asymptotic cone depend on the ultrafilter or not? And then to prove that, to deal with that, you have to actually do stuff in the group.
But it becomes like understanding like the local structure like is like HHG.
Yeah, so the local structure is, so picture that you're in, take z squared free product z and look at the asymptotic cone and stand at the base point. You're going to get a bunch of flats, like uncountably many flats at the base point. And then you'll also get some lines that come from the z's. And then you'll also get some extra archery stuff dangling off. And just that subspace is the local structure in the cone. And then you can sort of build this canonical real cubing by sort of gluing copies of that together. That's.
In the case of the asymptotic concept hyperbolic groups, the real tree that we get is universal in the sense that any other real tree of our continuum is asymmetrically embedded in that. Are these cubings of this kind?
Right, that's a good question. Yeah, so we didn't need to prove it for this, so we haven't written out a proof yet, but the expectation is that given a local structure that could have come from a group, the universal real cubing that you would construct from that local structure is universal for real cubings that locally look like that. So any real cubing whose local structure embeds in that one will embed in the universal thing that you're building. But that's a conjecture. I think it can be proved using the methods of this theorem, but we didn't write it down.
Was a real cubing a metric object or just a median object? I'm just trying to see how, like.
So it's a metric object because you just give it the subspace metric inherited from the L1 product. And that's a median metric because you're looking at a median subalgebra.
Why do you need to use Bowditch's thing once you know what the subspace is?
Oh, so right. So we started with the asymptotic cone of an HHG. At that point, you don't have any R trees. You don't have like anything. What we're not doing is taking the embedding of the group into the product of all the curve graphs and then trying to embed embed the cone in the product of the ultra limits of all those curve graphs. That like will absolutely not work. So we have to build the real trees after we know the cone is median, and the cone is not median when you just give it the limiting metric. You have to make it a median metric, and that's what Bowditch does for us.
Why does that naive thing break down there?
Right. So so the quick answer is that the real trees that that we construct, like that the thing projects onto, are not complete in general. So they can't possibly be ultra limits of curve graphs. I will draw you a picture later. Yeah, there's sort of not enough stuff. There's directions you can see that should survive in, say, the top level real tree, but you don't see them in the curve graph. You can write down.
Let's thank Mark again.